I just wanted to say just a minor thing, which is currently at Space Telescope Science Institute, I've shifted jobs. And so now I work in the Science Policies Group, which is responsible for allocating telescope time. And so that has actually become one of my responsibilities is managing the telescope allocation committee. So this is a very large committee of scientists from around the world that come and review the proposals that are submitted to be observed on the telescope. This is done through dual anonymous peer review. So I'm happy if anyone has any questions about how things get selected for the telescope, scheduled, all those sorts of things, I can also address those. But today I was kind of hoping to give you an update of sort of what's happened in the past 6 months, because really launch was on Christmas Day. And since then, we've had a 6-month commissioning period. Jwst is really complex. And so there is the deployment of the telescope, and then basically the focusing of the mirror, and then the checkout of the instruments, which culminated with these science data being taken at the end of commissioning. These data are owned by NASA rather than investigator groups that propose for projects on the telescope. So I'm going to tell you mostly today about these NASA observations, although I'll also sprinkle in some other things as well. So I want to just start off with this video. Let me see if I can start it. This is just downloaded off of YouTube. And this is showing the separation of Jwst from the fairing as it goes on its way into space to the Lagrange 2 point. And so this was really humanity's last view of JWST as it goes out, embarks on this journey to 1 million miles away from the Earth, beyond the orbit of the moon, to the Lagrange 2 point. Of course, it was launched by an Ariane 5 rocket. And as Deborah already mentioned, the launch, the ride that Jwst got was absolutely outstanding. The planned lifetime for the mission was 10 years, if you count the amount of hydrazine that was available for the rocket thrusters to station keep at L2. But the insertion was so good, essentially, that there was more fuel than budgeted available. So hence we have that 20-year lifetime for hydrazine now. So it's really, I think, changed the way that people thought about the mission. What you're seeing now is the deployment of the solar array. This was one of the first sort of really mission critical steps at the beginning, because Jwst, of course, runs on power, and the solar array produces electricity to run everything. So it was really exciting. There were lots of big chairs in the in the room when the solar array deployed, and we knew that things were on their way. So yes, everything about launch and orbit insertion just went absolutely beautiful. And that 20-year plus number was known pretty quickly after launch, definitely within about a week. And so, just so excited that there's the potential for so many years of Jwst observations. So I just wanted to have a quick refresher here about what makes JWST special or different, distinctive compared to other observatories. We discussed last time about how JWST is an infrared telescope. And this is a diagram showing you the electromagnetic spectrum with the visible on the left-hand side. You can see that rainbow, and that's the wavelengths at which Hubble operates. So mostly the wavelengths that our eyes see, but it goes a little bit shorter into the ultraviolet and a little bit longer into the infrared. And then there was the Spitzer Space Telescope that operated. It launched in 2003. It ran out of cryogen in 2009, but it really worked deep in the heart of the infrared from 3 microns to 160 microns. And you can see JWST sits in the middle between Hubble Space Telescope and Spitzer Space Telescope, working at about a 0.5 micron. So that's, the wavelengths that our eyes see, but it goes all the way out to 28.5 microns. And also as another reminder, this is just a schematic showing you a comparison of the primary mirrors for the Hubble Space Telescope and for the James Webb Space Telescope. Hubble on the left is a monolithic mirror, so it's one solid piece of glass. You may recall that Hubble was launched on the space shuttle, and that's how it got into its position in low Earth orbit. On the right-hand side is this nice cartoon showing you what the Jwst primary mirror looks like. And you can see that there are all of these individual hexagons. These are the individual segments that together make up the primary mirror. And this was necessary to do to make one big mirror out of many little mirrors, because Jwst is so big that it doesn't fit in the nose cone of a rocket. And so it has to be folded up so that it can be launched into space. The other key thing that you'll note is the color for the two. Jwst is made out of a different material. The primary mirror is made out of a different material from the Hubble mirror. The Jwst mirror is made out of beryllium because it doesn't change its shape at low temperatures. And the primary mirror is at about 40 to 50 Kelvin. And then the other thing that you notice is this gold color, and that's because the surface of these mirrors is coated in gold because it is extremely reflective in the infrared. So one of the things I thought would be really fun to see would be the process of how they get those 18 mirrors to work together and act as one. So I'm going to show you a series of movies about how they did that. So the first one here is called segment finding. So this is pretty much what they saw when they first looked at the sky with the telescope. Basically, there are 18 splodges of light. Each one corresponds to one of the segments. And you can see that they'll wiggle a segment and that makes one of the splodges wiggle, right? And so that allows them to figure out where each segment is pointing on the sky. And then after they do that, the idea is to bring those different points of light together into the same geometry and configuration that they're actually in on the telescope as the first step to aligning the mirrors. So you can see all the segments have names like a letter and a number coded together. And the wing on the right, you can see vertically as you go down, starts at B2, then goes to C2 and B3. And when you look at the end of segment finding and you look at the order of the these splodges on the sky, on the right, you see B2, C2, B3, just like physically happens on the mirror. Okay, so here's the second one. And what this one is showing is basically once you have the coarse images of the star, they're kind of out of focus. And so the first job is to first order, try to focus them so that each segment appears as a point of light. And so you can sort of see that process happen here. And then once that sort of adjustment is made, then the next step is what's called stacking. All right, so the next, this is step 3 now, and it's called segment stacking. So essentially now you have focused pinpoints of light, more focused pinpoints of light from each of the segments. And the idea is basically just to co-locate them so that they're all one on top of another. So the idea is that the starlight is shining onto the segment, and the segment is pointed well at that secondary mirror at the top, so that then the light shoots down that tube into the telescope and eventually to the detector. And so the top here shows you a detector image of what the stacked segments look like. And then at the bottom is sort of a 3D representation of the intensity of the light. So the square at the bottom shows you the spatial area on the sky. And then the height then shows you the intensity of the starlight. And so you can see that everything is, the images of the star at each location are one on top of each other, so they're adding up. But this doesn't necessarily mean that those images that they're in phase with one another, that the light is adding coherently. And so the next step is called coarse phasing. And this is done using an interferometric technique where they interfere the light from 2 adjacent segments. This is actually a spectrum of interfered light. And you can see here as they adjust the height of the segment, how that changes the appearance of this interferogram until they're aligned. And so basically all the segments are paired. And you can see that as you do this coarse phasing, how the intensity, like the height of that peak of the star, increases as you are phased. So the end goal was this really beautiful image that was shown. This was really unexpected. As a person working on Jwst, essentially we had been told ahead of time that really nothing was going to be released to anyone until we got till July. So it was really, I think, surprising and just a really nice indication of how well things were going during commissioning when this telescope alignment image was shown. So this was after the whole telescope is aligned and all the segments are working together as one. So there's kind of a before and after picture of the mirror that's shown on the right-hand side. So the NIRCam camera can actually be pointed in a way backwards to look at the mirror. And you can see at the top, there's an image here where only one of the segments is lit up. And that's because only one of the segments was pointing at the star. But then after the mirror alignment, you can see that the selfie looks different. You see uniform illumination across all of the 18 segments, indicating that they're all working together. One of the really amazing things about, even from early on in the mission, about these Jwst images is how sensitive they are and how far back they can look in time. This image that is shown here was taken pretty quickly. It's not staring at the sky for a long period of time. And already you can see all sorts of things popping out in the background, lots of beautiful spiral galaxies. And indeed, when we were looking at the Hubble Deep Field last time, we noted that you could tell the difference between extended objects like galaxies and stars, because stars are spatially unresolved to the telescope and they have a diffraction pattern. So with James Webb Space Telescope, it's a hexagonal mirror. So there's a six-fold symmetry. So point sources have this sort of six-fold symmetry in their the diffraction spikes. And so you can see the very bright star in the foreground that's used to focus the telescope. And then you can also, if you squint and look carefully, you can see there's a couple, maybe a few more stars in the field, like half a dozen or so, and they all have this sort of starbursty pattern associated with them. But pretty much everything else in the image is a galaxy instead. So everyone was super excited when even just these first focus test images were coming down from the telescope. One of the things that I just wanted to mention really quickly, you may have seen some press about the telescope being hit by a micrometeoroid. Before the mission, it was known that there were going to be micrometeoroid impacts. So essentially, these are bits of dust and other things that are, in our solar system. So for example, if you think of comets or something coming from the outer solar system into the inner solar system, they sublimate and they release dust particles. Asteroids collide, they create dust particles. So there are these dust particles with varying compositions that, we expect to hit the mirror every so often. And Jwst is different from Hubble because it's not protected in a tube. And so we knew that there would be these micrometeoroid strikes on the cadence of about every month or so. And that's pretty much what has been seen, since launch and deployment of the telescope, is that every month there is a micrometeoroid impact that's at the level that can be detected. So these are interferometry measurements showing the alignment, the surface of the mirrors. You can see sort of a baseline one on the left-hand side and another one on the right-hand side after this very large event that happened sometime between May 23rd and May 25th. And you can see on the bottom right, there's a bright spot sort of next to one of the struts, which is showing sort of, this micrometeoroid ding. So we don't have very much information about these strikes other than how they impact the ability of the mirror to focus. So really what we know is sort of about the kinetic energy. And essentially this one was more energetic than the typical ones that we see by maybe a factor of a few. But the level of damage from the micrometeoroid impact is still sufficiently small that the overall performance of the telescope, can compensate for it. And so it's still performing still well above expectation or design despite this strike. So, it was a larger than expected event. We don't know if essentially Jwst just got unlucky and had a larger event early in the mission. This happened with Spitzer. In that particular case, they were really concerned about coronal mass ejection events from the sun because those send a lot of protons toward the observatory and degrade the detectors. And Spitzer experienced a very large CME early in its mission, and people were concerned about how the detectors would hold up over time. And it turned out that basically there was no other event that was that large again. And so it had basically its whole lifetime dose at the beginning. So we don't know really, and we'll find out. It's a little bit of an experiment to figure out what the space environment is like at L2. Okay, so one of the things that we talked about last time was what science do astronomers expect to do with JWST? And I told you a story about how JWST was approved as a mission in the 90s. And this was really based on the ability to look back in time and see the first galaxies. And this schematic shows you a comparison in ability to look back in time among different facilities. So at the top, you see 1990 ground-based observatories. And then the next ones down are different variations of the Hubble Deep Field, where Hubble has stared at different patches of the dark sky to try to look back in time with different instruments, because Hubble's instrument package used to get upgraded every few years. And so it would give it more and more capability. And so one of the reasons why JWST was being built was be able to look further back in time and to see things that were, as the universe looked 200 million years after the Big Bang at a redshift of about 20 or so. And the first images have been really spectacular in showcasing this ability of JWST to look back in time. This is one of the early release observations. It is they're calling it JWST's first deep field, but it's a galaxy cluster, SMACS 0723. And this movie that I'm trying to show you is basically first showing you the HST picture of this region in the sky, and then it shows you the JWST picture, and you see the brightening and the increase in detail that can, as you go from one to the other. So this is really the reason why JWST was built. And the thing that's so amazing about this is this observation of the galaxy cluster, all the different filters, everything was done in about 12 and a half hours compared to like weeks of time with Hubble Space Telescope. And so this just demonstrates the power of JWST, that it can do in hours what Hubble used to do in days. And so I just love looking at this picture. It's so beautiful. You can see, again, the stars here because they have that starbursty pattern. But this is a galaxy cluster, and it's showing lensing. So essentially what's happening here is that there is a cluster of galaxies. So, it has a lot of mass, and it acts as a gravitational lens for galaxies that are behind it that are further away. So gravitational lensing means that it makes those distant galaxies appear brighter. And it also, one of the effects is to sort of distort them and show multiple images. And so here, this arc, for example, that you see, this is a galaxy that's behind the foreground cluster, which is being lensed. So it's being made brighter than it should be. And then you can also see multiple images. And here's another cluster here. Or I'm sorry, here's another galaxy that's being lensed here. So the remarkable thing about this is just even in such short of an amount of time, the number of galaxies that you can see in this image and the amount of detail that you can see. So for example, you can see in some of these galaxies very clear structure, spiral arms, barred centers. This sort of looks like a string of pearls, like maybe you're looking at an edge-on disk galaxy and you're seeing discrete star-forming regions. So, the number counts of galaxies is really impactful. And then also understanding all the different morphologies over time helps people understand how galaxies evolve in time from, the very distant universe, the first galaxies at 200 million years after the Big Bang. So these images alone would be remarkable, but the really wonderful thing about JWST is that, well, first it takes images and it does them at many infrared wavelengths, but it also takes spectra. So what I'm showing you now is a comparison between, on the left, the NIRCam image, and MIRI on the right-hand side. This is in the mid-infrared. This is more like 10 or 20 microns, where you're able to see heat from dust in the galaxies. But what I really want to show you are the spectra. So the amazing thing about JWST is it has the capability to take spectra of many objects in the field at the same time. The workhorse camera, NIRCam, that's the image that you see on the left. It's taken with NIRCam. But there's a workhorse spectrograph called NIRSpec, and it has what's called a microplexing capability. That means that essentially you can take spectra of many different objects in the field at the same time. And that's what this is depicting, is essentially a spectrum from this galaxy here, this galaxy here, this galaxy here, and with little zoom ins of what the morphology, what the geometry of those galaxies look like along with their spectra. So this is really powerful because the spectra are really helpful for telling you what the exact redshift of the galaxies are, and therefore what their distances are. And so the way this is done is by looking at the chemical fingerprint of the galaxies. So you can see there's labeled here emission lines from hydrogen, oxygen, and there's a little neon emission feature in here too. But by looking at the pattern of these emission lines and recognizing them where they are at different wavelengths, you can calculate what the redshift is. And so these examples that they've pulled out here are galaxies at different redshifts, different distances, different times after the Big Bang. And you can see that the one that is the furthest and the soonest after the Big Bang has the largest redshift. Those features are shifted to the longest wavelengths, whereas the relatively closer one is shifted less. So it's absolutely remarkable here. The one at the top, the closest one is 11.3 billion years after ago is we're seeing the light now. This one is we're seeing the light from 13.1 billion years ago. So this is already 400 million years after the Big Bang, just out of the box, without staring for weeks on end in just 12 and a half hours of exposing. So it's just been absolutely remarkable to see. So, they get lots of spectra covering 1 to 5 microns for NIRSpec, and then for MIRI 5 to 30 microns. And that previous slide just showed a snippet of the spectrum. This is a slightly larger part, but it's showing you that you get quite a bit of compositional information. So you get many lines, emission lines from hydrogen, oxygen, and neon. And this is really important for finding out not only the composition of the gas, but then understanding the excitation temperature. How hot is the gas? Other things that are super cool that people have been able to do is they can take spectra of different galaxies in the field. We had been looking at this arc here in these two different parts and postulating that this is a galaxy behind the cluster that's being lensed. And so these are really two images of the same galaxy. By performing spectroscopy on these galaxies, you can confirm that this is true. And so you can see these are snippets of now nearest spectra instead, but essentially spectra in the near infrared still, showing that the spectra of these two arcs is the same. So confirming that they are indeed the same galaxy that's being gravitationally lensed. And then there have been just outstanding discoveries that have been made by members of the community as JWST has entered regular operations. So it has started taking data from its normal science program. So investigators are getting their data, including these early release science programs. These were programs that were selected years ago to basically exercise the different capabilities of the observatory, looking at typical sources, and they were selected through peer review. So there are different teams working in different science areas. So this is one of the examples of the early release science, where a team has been looking through a different deep field, and they discovered this galaxy, which they have named Glass Z13, because they think it's at a redshift of 13. This is not part of their early release observations. So right now they just have NIRCam images of this galaxy, so they can measure brightnesses for it at different near-infrared wavelengths. And the next step for them will be to get spectra to confirm whether or not that redshift of 13 is correct, and then to look at the chemical fingerprint of the galaxy to understand more about its evolution. So you can see in this particular field that these are really, truly high redshift things that people are now beginning to find. And I personally can hardly keep up with the flood of new papers that are coming out. I saw on AstroPH, the archive server the other day, that, people have started finding galaxies that they think are a Z of 20. So again, going back and supporting the original science case for why James Webb Space Telescope was built. So it's just absolutely tremendously exciting to see. And another thing I talked about with the infrared is that it has the ability to see through smoke and detect heat. People use infrared cameras, for practical everyday applications. And so on the left-hand side, you see a picture of a firefighter looking at a smoke-filled room, right? And it's really hard to see what's going on. But on the right-hand side, this is an infrared picture of the same scene. And now the infrared light, because it has a longer wavelength, can pierce through the smoke, the small particles, so you can see further. And then the other thing that it's sensitive to is heat. And so you can see the body heat from the person on the floor. So the same principle applies to astronomical observations, where the infrared can be used to sometimes see through dust, and then also see heat from objects as well. So the second ERO that was super exciting is this observation of Stefan's Quintet. This is a grouping of 5 galaxies on the sky, which you see on the left-hand side with, this is a Hubble Space Telescope image. You can see that 2 of the galaxies in the middle, they're interacting. So they're so close that the gravity from one is affecting the other. And so it looks like maybe this galaxy is ripping off material from this other galaxy as well. There's another nearby galaxy at the top here, which looks like it might be interacting with these other 2 galaxies, but it's a little bit hard to tell. And then on the left-hand side here, you see something more like an elliptical, perhaps galaxy, where these are clearly barred spirals. And this one has a really distinctive color compared to the others. You see a lot of blue stars here. So the picture is a little bit different as you go into the infrared. This is now JWST NIRCam. And now you're being able to see not only the stars and the star formation, but to peer through that and to focus on the dust. And so you're starting to see the heat from the dust in the galaxies. So, for example, in our Milky Way, in between the stars is the interstellar medium, and that's dust and gas. And typically there's 100 times more gas than dust. And the main constituent in the gas is molecular hydrogen. And you can see here that this top galaxy really looks like it's probably interacting with these other 2 galaxies and triggering star formation nearby, where the 2 are influencing each other. So you can imagine basically the 2 outer parts of these galaxies crashing into each other. And as they do so, the gas density and the pressure goes up, and that can trigger star formation, which is probably happening in this ridge. I should mention that while this string of galaxies here, they're all probably at the same distance. That this particular galaxy is actually much closer and not physically associated with the others. And that partially accounts for its differing appearance. I think this one is maybe more like 40 million light years away, and these are more like 250 million light years away. You can do the same thing and go further out into the infrared. And again, really see the thermal emission from the dust in the galaxy. And so just these really beautiful structures that are seen with MIRI. But again, I'm super excited about the spectroscopy, so I'd like to show you the spectra. Just like we can take spectra in the near infrared with NIRSpec and NIRIS, the MIRI instrument has the capability of taking spectra in the mid-infrared. And it does this basically with, it's called an integral field unit. But essentially what it does is it gives you a spectrum of all the different points in the field. And so from this particular data set, they've been able to extract a spectrum at this location at the very center of this galaxy, and another one that's a little bit offset. So the center of this galaxy is a really interesting location because it turns out that the center of this galaxy is host to an active galactic nucleus. So this is a supermassive black hole, which is tens of millions of solar masses, which is accreting and feeding on the host galaxy. And so essentially this pointing at the bottom is toward the active galactic nucleus, and the one on the top is more of the host galaxy. So you can see that there are a number of commonalities between the two. This is probably the host galaxy. So you can see these emission lines, molecular hydrogen, iron, argon, neon, all of these different elements. But then also you can see that there's a difference in the very central position, that the overall shape of the spectrum is different, that you're seeing more emission at the longer wavelengths, indicating a hotter kind of environment. But then what to me is super cool is that you see a dip in the overall level of the amount of heat that's coming from the galaxy. And this shape is really distinctive. It's telling you about the material that's along the line of sight. So active galactic nuclei are thought to have basically disks around them, or toruses around them. This is sort of like so they have an accretion disk where, basically matter gets backed up before it falls onto the black hole. And then just beyond that is a fluffy torus of gas and dust. And so what's probably happening here is the line of sight. So when you're looking at the center of that galaxy, the bright center of that galaxy is producing this heat, but then the fluffy torus is getting in the way. And so you're seeing absorption due to the silicates in that fluffy torus. So you're seeing what the areas near the black hole, not right in the accretion disk, but just outside, are made out of. And this silicate feature is really distinctive because it tells you the composition of the silicates, whether it's magnesium rich, iron rich, and it also tells you about the size of the particles and can give you insight into the detailed physics of what's going on in that region. So I think it's super cool. The other way that you can visualize this data is to take slices of the cube instead of taking a spectrum all the way down. And so basically what you're seeing here are essentially the way the data gets formatted is you have two spatial directions. So this is an image, but then it's an image taken at a number of different wavelengths. And in this particular case, it's probably hundreds, thousands of wavelengths, depending on the amount of spectral resolution that the observer asks for. So you can image the area, in specific atomic or molecular lines. And so that's what this is depicting at the bottom is you can ask the question, like spatially, where is the atomic hydrogen emission coming from? Where are the iron ions? Where's the atomic hydrogen? And that's what these maps are showing you. This particular data set happens to be taken with the NIRSpec IFU instead of the MIRI IFU. So it's at wavelengths between 1 and 5 microns. But you can do the same thing with the MIRI data that we were looking at previously. You can format it into the cube and look at images at different wavelengths. So what I think, again, is really cool, so you get this very detailed compositional information, but you can also go one step further. And because these lines are very narrow, you can measure red shifts for them, or Doppler shifts for them, to understand their velocities and do what we call kinematic studies of these galaxies. And so essentially what you're doing is we have the light all spread out, and the argon emission, for example, comes out at one, it's supposed to come out at one wavelength. But you can imagine if the gas is coming towards you, it's a little bit blue shifted, and if it's moving away from you, it's a little bit red shifted, just like those distant galaxies, but on a smaller amount of redshift or blue shift. And so you can build these maps that are showing not just where the argon ions are, but what their motion is. Are they moving towards us or away from us? To again get at the detailed motions of the gas and how that black hole at the center is being fed. So these are really new observations, so people are still in the process of trying to analyze them and understand what all the data means. But in the meantime, I think the amount of information here is absolutely amazing, and it's just spectacular to see how JWST is changing our understanding of the universe in real time. So the next object that I wanted to move to is the Southern Ring Nebula. So for this particular one, they did not take any spectra, but there are these really beautiful images, again, with Hubble on the left and JWST on the right. This now is a planetary nebula. So a planetary nebula forms at the end of a star like our sun's life. So if you think about the sun, right now it is burning hydrogen into helium through thermonuclear fusion in its core. And over time, when it exhausts its hydrogen fuel, it will start burning helium and on up through heavier and heavier until it hits iron. Once it gets to iron, it's no longer energetically able to fuse iron atoms together. And so thermonuclear fusion in the core stops. And so at this point, there's no more energy being produced that supports the core against its own self-gravity. So essentially it collapses and it rebounds. But in this process of forming what will be the white dwarf at the center of this planetary nebula, it ejects and puffs out the outer layers of the star. And so that's essentially what's being seen here in this Hubble image, and is also seen in the JWST image. So you can see a bright source in the middle, which is actually, this is actually a binary system, with the stellar remnant is actually the fainter object, and it happened, which is actually a main sequence star. But you can see these outer layers of material that have been ejected from the evolved star. And then it's absolutely spectacular. We'll switch to look in the infrared, and now you can see the full, a greater extent of the dust and all of the fine structure in the dust, to understand, if you're thinking about the star puffing away its outer layers, then that means that the ones that are further away were ejected longer ago than the ones that are closer. And so you can study these later phases of stellar evolution by looking at these structures in the planetary nebula. So super cool. The other thing that this just highlights is it's looking at a really bright object in the Milky Way, and yet we see all of these distant objects even in this fairly fast observation. And one of the things that was noticed in here was essentially this linear feature. And some of my colleagues were taking bets early on about what this was. They thought it might just be a filament in the planetary nebula structure, but it turns out that it's actually a background galaxy, which happens to be edge on, and just happens to be, in projection, close to this planetary nebula. So super neat. And just like before, we can go and look at this object at longer wavelengths. You can see the galaxy is still there here. And you can see the brightness of the stellar remnant is picking up, and it's more equal in brightness compared to its main sequence companion here. But just really beautiful structures that I'm sure that we'll be spending lots of time studying to understand stellar evolution. The last time I came to talk to you, we also talked about how Jwst was expected to revolutionize our understanding of exoplanets. And the plot on the right-hand side shows all of the exoplanets that are going to be observed in the first year of operations. Across the x-axis, this is equilibrium temperature for the planet. Confusingly, the high temperatures are on the left side and the low temperatures are on the right side. So it's meant to imagine that the star is at on the left-hand side here, and things that are close to it are hotter, and as you go further away from the star, it becomes cooler. So you can see here, like Earth is right here at it shows more than 300 Kelvin, and then Jupiter is up here. And so Jupiter is to the right because it's further away and colder than the Earth. And then the y-axis is showing planet radius. So with larger up and smaller ones on the bottom. So you can again see the separation between Earth and Jupiter, because Jupiter is of course much larger than the Earth. And you can see the variety of planets that Jwst is going to study in cycle 1. Objects that are like Jupiter in our solar system are like Earth in our solar system, but then also these lava worlds, which are basically Earth-like analogs, but they're so close to the sun that the surface temperature is super hot. It's like a couple thousand degrees Kelvin. So this is a temperature at which like rocks melt. And so that's why they're given this moniker of lava worlds. And then you can see at the top here, these hot Jupiters. These are Jupiters that are at very close in orbits inside the orbit of Mercury in our own solar system. And so they get a lot of insolation, a lot of radiation from the host star onto the planet, which absorbs this energy and puffs up. So it makes these Jupiters sort of puffier than our own Jupiter. So one of the objects that was studied in these early release observations, or for which observations were taken, is a star called WASP 96b. It's a hot Jupiter, so is in family here, sort of between these two red dots. It's less massive than our own Jupiter, about half the mass. But as I was mentioning, it's inflated. So even though it's smaller in mass, it's fluffier, so it's 1.2 times the size in radius, and it's very, very close. It's within 0.05 AU of the star, so its orbital period is super fast. It's 3.4 days, and it's on a very circular orbit. So probably the most popular method for studying exoplanets with Jwst will be transits. This is when the exoplanet passes right in front of the host star. And so the rocky core, for example, will block out light from the star, but light will be able to filter through the atmosphere. And then you can also study, that's transit when the planet goes in front, but you can also study eclipse when the planet goes behind the star, so that you're looking at systems where, or observations where you're seeing star plus planet, and then you take away the planet and just see the star. And so you can figure out what the planetary emission alone is. So this is the early release observation of WASP 96b. And so again, this orbital schematic showing the planet going in front, and the light being able to, so the core blocking out the light from the star, and some of it filtering through the atmosphere. And so you can see that these are measurements of the brightness of the star with time. And so you can see as the planet starts to pass in front of the star, the brightness dips until it's fully passed and crosses over to the other side. And these observations are absolutely exquisite because you can see how small these error bars are, the precision to which they can measure the change in the brightness of this system over time. So you can see the star plus planet is at 100%, and then the depth of this transit is a little more than a percent and a half or so, and yet it's measured to such high precision. So this is what's called a white light curve. So this is showing you the effect of the transit on all of the light that's detected by one of the spectrographs. But the spectrographs actually disperse the light in wavelength. And it's done so that you can try to look for signatures of atom molecules. And so this is a plot showing then the amount of light that's blocked by the planet as a function of wavelength. And what's really interesting, so you can see the little measurements here, these error bars, and then a fit to it, which is this sort of blue line. And what's amazing is that out of the box, without too much effort, you can already see these bumps and wiggles that are indicative of water vapor in this planetary atmosphere. This planet, the planetary atmosphere, I think has a temperature of maybe 1,000 degrees Kelvin. So certainly a temperature at which water is vaporized. So you're seeing this water vapor in the planet's atmosphere. And then the last really fun thing that I thought I would just show you is this picture of Jupiter that was snapped during commissioning. This was not an early release observation. This was an observation that was taken to exercise solar system observations. So solar system observations are a little bit different from observations of stars because planets, as you know, are wanderers and they move across the sky. For the telescope, because it has to slew at the same rate as the moving target to be able to observe it and keep it in the same place in the field of view. So this was a very fast exposure, 75 seconds, just to show that Jwst could observe moving targets. And already there is new science that people have found in this very fast first observation of Jupiter. I've tried to highlight some of the features in here beyond Jupiter itself. This is Europa here. And then what was amazing is that the rings around Jupiter could already be seen in this very fast exposure that I think was totally unanticipated, although the rings were known to exist ahead of time. The other thing that's new and was totally unanticipated and is actually total science is this sort of red glow, and you can see here of what looks like an upper sphere discovery that scientists are trying to understand. And what's really super cool too is not only do you see it very clearly, but also you can see what appear to be these sort of waves in this interaction in the atmosphere here. And that's thought to be an atmosphere the atmosphere interacting with Io, which is, releasing material through its volcanic eruptions into the local environment with Jupiter. So that material is interacting with the Jovian atmosphere and producing this wave sort of structure. So just amazing, fabulous science, and, we can already see how Jwst is beginning to transform our understanding of the universe. So, we have so much to look forward to. It's absolutely amazing, how much science that I think Jwst is going to return. And I just wanted to give you a little taste of how operations work on the telescope. The way that the telescope is scheduled is essentially, when all of the observations get selected for an upcoming cycle, there's a team that goes through and makes sort of an annual plan. And then as we get closer to those observation dates, there's a short-term scheduling team that goes in and pulls observations and makes the exact schedule that the telescope's going to execute. These short-term schedules are actually posted on the website for Jwst, so you can look and see what it's looking at any given day, which I thought was kind of cool. And so I've highlighted in yellow what's being observed today on July 28th. I just thought this was really cool that today Jwst is looking at Jupiter some more. And instead of taking images, I think that was a NIRCam image of Jupiter, it's going to be doing Miri spectroscopy. So that's at the mid-infrared wavelengths, so 5 to 30 microns instead of 1 to 5 microns. And it's going to be doing spectroscopy again. So basically it'll get one of those image cubes where you see a picture of Jupiter at all of these different wavelengths, including in molecular and atomic lines and things like that. So it spends time doing that. You can see on here, there are stars and brown dwarfs that it'll go to after looking at Jupiter. And then it'll go to for example, galaxies. So in this particular case, it's going to look at Andromeda. Andromeda is so big on the sky that essentially you have to step the Jwst imagers across it, mosaic it, in order to cover the whole galaxy. And so I think that's what this 1, 3, and 14, these are probably different tiles within the mosaic so that you can cover Andromeda fully. With, it looks like they're doing NIRCam imaging and nearest imaging as well. So again, near infrared imaging here. So super, super exciting. And this is just the last image that I wanted to leave you with, which I think is absolutely spectacular. This is the Carina Nebula, and it's being called the Cosmic Cliffs. So this is a star forming region. And what's sort of off the scene on the top here is there are massive stars that have been recently born in this stellar nursery. They're very high mass stars. They produce a lot of UV radiation. They're very luminous. So, you know, they also produce just a lot of energy. And that shines onto the local interstellar medium from which they formed, and it blows this bubble. Not only does it blow this bubble, but it also ionizes gas, you know, in this cloud of gas and dust. And then that ionized gas also gets heated up in the, like, you know, as the gas gets photodissociated, molecules get broken apart and then photoionized, get ionized by that radiation from those massive stars. So the ionized gas becomes very energetic, very hot, and it starts evaporating. So all that sort of wispy structure that you see there is actually evaporating ionized gas coming off of this star forming region. And as you look into the star forming region, you can see little baby planetary systems being formed. These red things are stars that are enshrouded in dust, you know, right close to the star. And so they're, you know, really protostars with disks around them that are forming planetary systems. But this picture that we get from Jwst allows us to peer more deeply into the heart of the Carina Nebula than ever before to really watch this process in action. So it's such a beautiful image that I thought that I would stop here and leave you with this just beautiful image of the Carina Nebula. So thanks for your time and attention. I'm happy to take questions.
To go back to gravitational lensing, my understanding is that you're seeing multiple images of only one galactic object.
That's correct. You got it just right. So in this particular case, what's happened is there's a cluster of galaxies, and the cluster of galaxies, if you add up all of the mass and all the galaxies in the cluster, you know, that's a lot of stuff. And it's so massive that basically it can distort light from things that are behind the galaxy cluster. So what I didn't show, I couldn't find, is basically that, you know, they have the spectra not only for these arcs here, but then also this here. And when you look more closely, maybe it's easier to see, I think it's easier to see perhaps in this image. But essentially what happens is that the spectra, and when you look at longer wavelengths, I think the colors of this arc and this arc are different. So it's actually telling you that there are two galaxies that are behind the galaxy cluster that are being gravitationally lensed. Yeah. It's a trick that people have used, for example, with Hubble to study very distant galaxies, because like with the deep fields, you can only stare so far back in time. And so one way to try to stare back a little bit further is then to use these galaxy clusters to lens things that are behind the galaxy cluster, so you can look just a little bit further back. And so I know Hubble had this treasury program several years ago where it focused on looking at a dozen or so of these galaxy clusters to look at these very distant galaxies that got lensed by the cluster, to really try to push back as far as you can to look at just the most distant things you could with Hubble. And of course, you can play the same trick with Jwst too. And so it'll be interesting to see, you know, what people learn from, you know, relative strategies, both the deep fields, so just staring at what looks like a blank field in the sky, so that there isn't foreground contamination from nearby galaxies and trying to look really far out. That's one strategy. To this other strategy where you look at these galaxy clusters trying to catch lensed objects that are behind the galaxy cluster.
Christine, doesn't the lensing also tend to confirm one of Einstein's theories of relativity?
Absolutely, yes. And this isn't the only kind of lensing that's seen in an astronomical context. There's also microlensing, which is a technique that's becoming more popular for studying exoplanets. It's a way to statistically study a sample. So in that particular case, what people do instead is they stare at the bulge of our galaxy. So, toward the galactic center where there's, a lot of stars in the field. And then you can imagine with the motion of the galaxy, the stars are moving relative to one another. So sometimes like one star passes right in front of another star. And so the foreground star can lens the background star. So when it lenses the background star, again, you see this profile where basically the brightness of the star goes up and then comes down as the, one star crosses in front of the other, and the foreground one lenses the background one. Sometimes they see little blips in that brightness profile, and that actually indicates the presence of planets around the background star. So that's called microlensing, and it's a way that people can, by staring at lots of stars at once, try to aggregate statistics about, planets in general around stars. The one minorly frustrating thing about it is, the only time that you can really study that planetary system is during the lens event. And then when the lens event is over, it's hard to go back and, find out more about the planetary system. But that's another use case that's similar, using lensing to study things that are more distant.
Christine, how many telescopes are there on the James Webb Space Telescope?
So Jwst is really, I would call it one telescope, right? So I don't think I brought a picture of, right? So this is, so when I think of a telescope, I think of one primary mirror, right? So the way that it has this ability to look in different ways at the universe is through different instruments. So I didn't show it here, but essentially the light goes, basically from the telescope, gets split up and gets fed to 4 different instruments, right? And so the different instruments have, different capabilities, right? So yeah, I probably should have described this a little better, but essentially, one of the instruments that the light gets split off to is called NIRCam, the near infrared camera, and that's the workhorse camera for the observatory. So basically it works at 1 to 5 microns. It covers like a fairly large region on the sky, like an arc minute by a couple arc minutes. And so, you can make beautiful mosaics and stare very deeply at the sky that way. But if you want to do spectroscopy, in the near infrared, you can't use NIRCam perhaps. So you might want to use NIRSpec instead. And so NIRSpec is really a spectrograph. And so it has dispersing elements in it, like prisms that spread out the light. So you can take these beautiful spectra. NIRSpec and NIRIS basically have different ways of taking spectra. So NIRSpec has the traditional sort of classic way where you can put a fixed slit on top of like an object and just disperse the light in that slit. But you can also do other fancy things, as I mentioned, like with this micro shutter array. So this is actually a MEMS device, which is mapped onto the sky with actuators, gates that you can open and close individually, so that you can command them to open just in specific locations to take spectra at particular points on the sky. So that's how this particular observation was taken, was with that MEMS device and opening little slitlets is what they call them, but they're essentially actuator, they're gates, in each of these positions to get spectra at each of these locations. All of these instruments are super capable. So NIRSpec can do fixed slit, it can do this micro shutter wave spectroscopy, but then it can also do this integral field unit spectroscopy, where basically you have what's called an image slicer. So basically what happens is you can think of putting down a whole bunch of slits, like up and down, across this picture of the galaxy. And then each slit disperses the light from that slit, right? So it's getting spectra at each of these different locations. But then on top of that, the slit is long enough in this spatial direction that you get spatial information along the slit as well. So basically you can combine all of that to get what I was talking about here, which is an image like a cube, where you have, you can slice this cube up. So basically each slice is a picture, and each slice is at a different wavelength, so that you can image in like atomic hydrogen or iron or different things. So that's just NIRSpec alone, how the different ways that it takes spectra. Right. So there was NIRCam, the workhorse imager. There's NIRSpec. This is the workhorse spectrograph, also in the near infrared. There's NIRIS, which is a near infrared imager and spectrometer. So it kind of covers some of the same capability as NIRCam and NIRSpec. And then at longer wavelengths, there is MIRI, which kind of does it all. So it takes images in the mid-infrared. So now we're switching to 5 to 30 microns. So it's the one that took this beautiful image on the right of Stefan's Quintet. It not only does imaging, but it also does spectroscopy. It has an IFU, just as I was describing for NIRSpec, except for now it's 5 to 30 microns. So basically there's 4 instruments that go on the back, that are on the back end of the telescope, that can take data in different ways. And one of the things that's really exciting is that you can actually turn on more than one of these instruments at a time. So you can try and get down as much data as is valuable as you can. But we're a little bit limited in that there's basically like a hard drive on the computer. It's a solid state recorder. It's quite old. And so it doesn't have as much storage capacity as, things that are being built today. And so that's a bit of a limiting factor to like how much data can be taken and returned to the ground. So I don't know if that answers your question.
Yes, it does. Thank you. Will this spectra be able to find if there's water on a planet?
Yes. So that's exactly one of the key science questions that astronomers have, is what is the composition of the atmospheres of exoplanets? So right now with that transit technique, essentially people have been being able to see these dips in the light. They've been able to make measurements of, how much the planet dims the light from the star, at specific wavelengths, right? But this is the first time that there's enough sensitivity from an observatory to take a spectrum like this. So in the past, like there would be like maybe half a dozen data points here, right? But this is the first time that you can take a spectrum from 1 to 5 microns. Hubble tries to do this at visual wavelengths and in the near infrared, so maybe stopping at 1.6 microns here. But some of the strongest water features are actually at longer wavelengths. And so this is one of the reasons why we think that Jwst will be super powerful in that it basically provides this accessibility to a wavelength range that Hubble doesn't cover, where there are really important lines from like, water, CO, CO2, these are, molecules that are important, in our own atmosphere, and may help us understand what's the potential for materials that are important for life. in these other planets. This is not a hospitable planet because it's a hot Jupiter and its atmosphere is 1,000 K. But people are definitely going to try to push really hard to study the exoplanets, atmospheres of Earth-like planets with Jwst if they can. However, that's a sort of stretch science goal for this observatory. And so, every 10 years, astronomers get together and they try to envision what they want for their future. And so this exercise happened recently. This is called the Decadal Survey. And we recently had the Astro 2020 Decadal Survey where astronomers came together to try to think about what do they want as a new facility in the 2030s or 40s. And so the answer to that was sort of like a super Hubble. So a bigger Hubble Space Telescope, so operating in those visual wavelengths. And the idea was to basically be able to spatially separate out a planet from a star so that you don't have to use this transit technique, and to take the reflected light spectrum of the planet, because there's really important biosignature molecules in reflected light, at those wavelengths. So in order to make that leap to study Earth-like planets, you have to go to this direct imaging technique. And the reason why is because when you're studying exoplanets this way with the star and the planet lined up, you're getting a lot of light from the star at the same time. So you're seeing photons from the star and photons from the planet. And so the noise for your observation actually, it follows Poisson statistics. So basically, the more photons that you have, the more noise you have. It goes as root of the noise goes as root of the number of photons. And so what happens if you can get that star out of your field of view and just take the spectrum of the planet, you don't have the noise from looking at the star imprinted on your spectrum. And so, for those two reasons, the Astro 2020 survey, that's one of the killer app science cases for the next great observatory, is to take the spectra, the reflected light spectra of Earth-like planets and really push, really make it feasible to look for biosignatures on exo-Earths.
Christine,
No, no, no.
is there a limit to how far back we can view to the time of the singularity, the Big Bang, with this instrument or any other subsequent telescope?
That's a really good question, right? So one way to think about this is, so this is probably a nice graphic to look at. So we're being able to look further back in time, and you can see what this graphic is meant to depict is in the nearby universe, galaxies, they have this very ordered structure. You can see beautiful spirals and other things. And as you go back in time, they start to look more irregular. They're smaller, and these are perhaps the building blocks of what we see today. But there is some amount of truth to this graphic in that as you look further back in time, basically there's a limit to how far back in time that you can kind of look, right? So if you think about the Big Bang, there's a giant explosion, and initially everything was so hot that essentially it was a plasma. At some point, things had already cooled down a little bit, but you have sort of a soup of protons and electrons. And when you're in that phase, essentially, protons and electrons, they can have encounters, like one can fly by the other. And when that happens, you get a form of radiation called Bremsstrahlung, right? And so basically, in order to see visual light from the distant universe, you have to have a couple things happen. One is that all of that ionized material has to cool down enough to form atoms. Essentially, when that first happened, the universe was neutral. And then people talk about a phase called reionization, which means that essentially, from those, from that first neutral material, you could start to, build the first stars, the first galaxies. You could ignite thermonuclear fusion. And we think that those first stars, the first galaxies were really, really massive. So essentially they would have, radiated a lot of energy compared to our sun. They would have been very luminous, and they would have produced a lot of ultraviolet radiation, more so than our sun does. And so that combination of, just pumping all of this energy and particularly ultraviolet radiation into the environment would have caused what's called reionization. And so what we're looking back up to sort of, I think this epoch of reionization. So there are physical limits to how far back you can look in the visual because of bremsstrahlung. And really, there are these really beautiful observations that people have made in the radio wavelengths. So this is now the cosmic infrared background, which is seen at the radio. But essentially, this is that the whole sky to very high precision looks like it's just, I think it's about 7 degrees Kelvin. And this is the leftover residual heat from the Big Bang. And people, have learned a lot cosmologically from studying the structure of that cosmic microwave background. So in particular, the first experiment that I remembered was a satellite called COBE in 1994. Pretty much prior to that, all they knew was that, essentially it was this, 7K emission that filled the universe. And what was interesting about COBE was that was the first time that they could see fluctuations in the microwave background, and it was on, I think, 1 part in 10 to the 1,000. And so with that kind of constraint, they could start to constrain the cosmological models. So what is the overall geometry for our universe? Is it open? Is it closed? So does it, go on forever? Is it finite in size? People learn a lot about the very distant universe and the very first few moments after the Big Bang by combining, information at different wavelengths. So, yeah.
Christine, earlier in the week, NASA selected the launch vehicle for the Nancy Grace Roman telescope. Is there a plan?
Oh, you know more than I do.
Oh, it's a Falcon Heavy. But is there a plan in place for Webb and Roman to work in tandem once Roman gets an L2?
Yeah, that's a really good point. So, yes. So basically, in general, a lot of the observatories do try to have coordinated opportunities. So, so putting on my science policy hat, I can tell you that, for example, like Hubble Space Telescope at my institution has programs where you can apply for observatory time on more than one asset. So, for example, there are joint programs between Hubble and, for example, X-ray Observatory or XMM Newton, which is another X-ray observatory, and ground-based facilities such as are run by our own National Optical Astronomy Observatory. Jwst is going to provide some of these same opportunities in cycle 2. So not only those, but we're also going to be partnering with ALMA, which is the Atacama Large Millimeter Array. It's a radio observatory, and it has just exquisite angular resolution because it's a I forget, a very large number of antennas spread out over a large area in the Atacama Desert. So it's very sensitive. It has very wonderful angular resolution. So there are definitely science cases for which, people need to study objects on the sky at multiple wavelengths. And so, yeah, that absolutely, like, so for Hubble and Jwst, there's going to be opportunities to have those observatories work together. Some of those science cases require that you even observe the object at the same time. So you can imagine, like with these exoplanet transits, as the exoplanet goes in front of the host star, you want to study, like, all of the different molecular features. And so maybe you would want, wavelengths in Hubble in addition to Jwst or something like that. Or, if you're studying star forming regions, maybe you want, infrared and radio as well. But yeah, so these joint programs provide the opportunities, multiple things at a time, and even to look at them at the same time. So super exciting opportunities. And I'll say also with Roman, the institution that I work for, Space Telescope, is the Science and Operations Center. So it's currently the Science and Operations Center for Hubble and has been for 30 years. It is the Science and Operations Center for James Webb Space Telescope. And it will, it's one of the two Science and Operations Centers for Roman. So that work is actually divided amongst two institutions. So in California, JPL and IPAC, and then also Space Telescope on the East Coast. So I fully anticipate that there will be joint opportunities while, multiple assets are flying at the same time. Absolutely. Well, thank you so much for the opportunity and to come and talk to you today. I am super excited about the new observatory, and I hope I've been able to share that with you.